Hey folks, and welcome to Advent of Code in F Sharp day. What are we? 11. Um, as always, we'll be solving today's puzzle using the F Sharp programming language. So let's drop right into it. Puzzle has just unlocked, so let's take a look. Day 11, Dumbo Octopus. You enter a large cavern full of rare bioluminescent Dumbo octopuses. We have already saw bioluminescence this year. What's a Dumbo octopus? YouTube links are always dangerous to click. Meet the Dumbo octopus, okay. Oh, that's cute. It's a red octopus. Okay. They seem to not like the Christmas lights on your submarine, so you turn them off for now. There are 100 octopuses arranged neatly in a 10 by 10 grid. Each octopus slowly gains energy over time and flashes brightly for a moment when its energy is full. Okay. Although your lights are off, maybe you could navigate through the cave without disturbing the octopuses if you could predict when the flashes of light will happen. Each octopus has an energy level, which is something our submarine can remotely measure. The energy level of each octopus is a value between 0 and 9, so single digit. Here, the top left octopus has a level of 5, the bottom right has an energy level of 6, blah blah blah. We can model the energy levels and flashes of lights in steps. During a single step, the following occurs. First, we bump all the energy levels by 1. Then, if there's any octopus greater than 9, it flashes. And that sends out an energy level to all adjacent octopuses, including diagonals. Cool. If this causes an octopus to have an energy level greater than 9, it also flashes. This reminds me of a board game called Pandemic, where you have like diseases and cities become infected, and when there's an outbreak, it spreads to the neighboring cities. It's exactly the same thing. This process continues as long as new octopuses keep having their energy level increase beyond 9. But an octopus can only flash at most once per step. Of course, it only has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. It can never cycle more than once. Finally, any octopus that flashed during this step has its energy level set to 0. That might be something tricky. It might be tricky because say an octopus flashes, but all the neighbors flash as well, then the next cycle or the next step, that octopus that has flashed has to reset to 0 and not like have already like an energy level of 5 because or 8 because all its neighbors have flashed. Okay. Adjacent flashes can cause an octopus to flash on a step even if it begins that step with very little energy. Yeah. So yeah, say we have a 1 energy surrounded by 9s, then it'll get increased 8 times, so it becomes a 0 as well. And highlighting means it flashed during that step. And then we have a big example. Is it the same example? The 5, 4, 8 one? 5, 4, 8, yeah. Okay. Oh no. This is already a trickier problem. Okay, and we have to do this for literally 100 cycles. And we need to count the total number of flashes. Yeah, total number of flashes. Given the starting energy levels of the octopuses in your cavern, simulate 100 steps. How many flashes are there? Easy peasy. No, not really. It's something like a game of life, but it's game of life meets pandemic. I don't think I've ever seen a variation like this. Cool, let's try it. I'm first going to grab my own special input. Oh, is this correct? It's a really small... Yeah, that's a really small input. I was expecting a huge grid. That's either a very, very good sign that will be done in 20 minutes, or a very, very bad sign that I'll be here all morning. Is it just me, or does the example look bigger than the actual input? I'm going to put them side by side just for a second to verify. Let's grab it again. Or no, I'm just gonna put it in my old trusty example string. Let's parse both, or let's load in both. They are similar. Did it mention that the grid is a certain dimension? Yeah, they're always in a 10 by 10 grid. Okay. So it doesn't really matter which we take to start, but let's still keep going with the example in the today's puzzle, so we can follow along in case we encounter any bugs. Yeah, it's a 2D grid. We do need to track neighbors, so I'm gonna use the same approach I always use, which is a mapping locations to the octopus, or an energy level at least. Only thing I'm not sure about is that little detail where was it again? If an octopus flashes, then neighbors can flash and cause chain reactions. That's a bit tricky. How do we do that? Could do a very naive. No, I'm not sure how we do that. Usually, or in the game of life, a cell looks at its neighbors, like in the cellular automata. It looks at its neighbors, but that only looks at its neighbors to make a decision on what its own next state will be. But now, changing its own next state, like flashing in this example, has impact on the neighbors and could trigger chain reactions. It could also trigger chain reactions on points we already like visited. So I am maybe instead of just going over all the points, maybe we just need to do some kind of fixed point, or a while we have any work to do kind of thing, and just until we have no nines, and then we just like settle down the grid and we have processed a single step. Yeah, and then there's this little detail, you can only flash just the once. I think that's also a bit tricky. So those two are changes I've never seen before, and I'm not quite sure how we'll fix that, but let's cross that bridge when we get there. I think the general outline of the algorithm will still hold, so let's start parsing. Let's start parsing this into a grid. So I'm gonna alias the grid type. So it is a mapping locations to energy level. Okay, if we're going the type driven way, let's define all our types today. I'm not gonna make them like what am I trying to say? I'm not gonna do this. Am I not gonna do this? No, I'm not gonna do this. I'm not gonna make any mistakes mixing up locations and energy levels, so I'm just gonna make them type aliases. Like this. So it's just for documentation purposes. So our parse has to return a grid. It takes a sequence of strings and it returns a grid. So for every line, let's do the for comprehension thing again. So for row and column in lines when we index them. Let's do it like this. So for every row index and the line itself, do, and for every column index and the cell in line, we have the row column location, and we have the cell itself, which we can parse into an int again. There we go. And that's a single list. So we can push that single list into a map. If my keyboard will let me, at least. Maybe we also need to index, yeah, the line itself. I think this works. Let's verify whether it works by parsing the input or the example input. Nope, it does not work because cell is a character, and that just gives us the, what is it, the ASCII number instead of the sparse string. I had the same exact bug. I had the same exact bug. Whoa, it's early for me. Yesterday, but good part about having bugs more than once is you know how to fix them quickly, I guess. So first we have 5, then we have 4. Yeah, that looks correct. Maybe let's take a look at the second line. So after 2 2's and a 3, we have another 2. We just don't see it. I'm gonna trust the process here. We have a grid. And what was the terminology used to proceed? You can model the energy levels of flashes of light in steps. So we can do like an infinite loop or a specified number of loops by taking steps, and we need to do that for the full example 100 times. So I'm just going to start off by writing a function that takes one step, and then we can use that to start looping. So let's write a take step. Or let's play around in the REPL until we have the logic for a take step, and then extract that into a function. As always, we need to find the neighbors. Today we need to include diagonals, so I'm just gonna hammer out a find neighbors function, which takes a grid and a location. I used row and column in the parsing. I'm gonna use XY instead. I don't know why. I've always done it. No, I'm gonna keep row and column. That's more clear for me than an X that grows downward. So let's keep it like this. Diagonals we do need to do, so -1, -1, it's top left. What does it mean? I'm already confused with row and column stuff. So columns, rows are the first part. So if we need to go up, we need to decrease our rows by 1 and stay on the same column. Decrease our row by 1 and go 1 column further. So this is the deltas for our neighbors above us. These are the 2 next to us, and these will be the ones below us. My auto formatter will not like what I'm doing here. But anyway. I think it's something like this. So 0 and 0 to stay on the same row but look left and right, and then 1, 1, 1 to actually look below us. Does that look correct? Minus, minus, plus, 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 0, 0. Yeah, I think so. No, auto formatter says no. So goodbye. Self-explaining formatting. It was nice knowing you. What do we need to do with these offsets? We need to grab the deltas and apply them to the original location, and these are now the locations for all the neighbors. So let's look them up. And we can have, again, it's not an infinite grid, so once we're on an edge, we can have like no neighbors on the right. So we need to take care of that, and we can take care of that by doing a grid lookup, but using a try find instead of a find, which gives us an option, and it gives us none when there is no entry in the map. We've been here before. And instead of mapping, we can choose, so we get rid of the nones and extract the sum values. So this gives us a list of neighboring locations, right? Right, I think so. Let's give it a try. So let's do find neighbors of the grid, and let's try 0, 0, the origin. Oh, come on, print it out for me, thank you. We're already doing the lookup. Yeah, that's true. We don't need to do the lookup just yet. Do we? Do we not? This is like find the neighbor locations, and this other step is find values. I like to separate those. So let's call this find neighbor locations. And the second line is to find values in a set of locations or a sequence of locations. So that should give us... Yeah, okay, then it makes no sense to see what I did there. I'm going to, for now, if we don't need the neighbor locations, it makes more sense to show this and not leak implementation details like all the 9 neighboring locations where they don't even, where they might even not exist. So no, that looks a bit funky to me. Let's keep it as is. Do we have a 4, a 2, and a 7? A 4, yes. A 2, yes. A 7, yes. Do we need one more example to convince ourselves? I would like one more example to convince myself because of the auto formatting, getting rid of everything. Let's double check one more. So this should be 8. I'm gonna make it a list. I'm tired of not having a full list printed. And performance-wise, this will not matter one iota. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Okay. So I think we are looking at 7 now. So we have 5, 4, 8, 2, and 4, 5, 2, 6. Yeah, that's correct. So let's write our, what was it called again? Take step. Let's play around with take step. We know how to grab neighbors. And I want to rename this function really quick because now it is find neighbors again. We don't need the neighbors right. No, no, no. This is me on autopilot. This is not me solving today's problem. We need to look at every value, and then we need to flash if we have to flash. And if we have flashed, then we need to start taking a look at neighbors so we can increase their energy levels. I've solved this game of life thing too many times in my life. Sorry, this was autopilot. So instead of finding... Yeah, instead of finding values at locations, we do need to find the locations. So we'll have to fix this in a second, but let's first do the actual exercise. So I'm going to put a to-do here. And need locations. So I'm not sure whether we want to return all 8 possible locations or the X locations that do have values, so we don't drop off the grid, but that's a problem for later. So what will we do here? How will we tackle this? Will we just look for the first 9? That's going to be the safest, but also the most performance intensive. If I follow my usual strategy, Yeah, let's do something cool today. Let's write a fixed point operation. So a function that keeps looping and looks at two intermediate results. And if there is no difference, so it has reached a fixed point in its computation, then it just stops. So we're gonna fix point the grid until every explosion or every, what was it called, flash has occurred, and then we stop, and that is one step. That sounds cool. It sounds not the most performant. It's not the most performant approach, but just because it sounds cool, I want to try it. So we need to find the first 9 in the grid, or the location of the first 9. How do we find the first something in a map? It's not a lookup by key. So actually our map data structure only makes sense to find neighbors. It's not really useful. We could do a map.filter. We could do a map.filter, but if we're filtering and then just grabbing the first element, I'm not convinced that map is the correct data structure again, but that's not a problem. Or at least it's not a problem until it becomes a performance problem. Let's try to find the first. Try to find is the correct word here, because we expect this to not work at a given time. When we have no 9s, the step is complete. So this is location and a value, where value is 9. Those are the ones that need to blow up, right? I'm saying blow up, but it's non-lethal. They flash. Greater than 9. See, that's the point where I'm not really happy. If we do take greater than 9, we also need to keep track of this octopus has already flashed this step, and I don't really want to do that. I don't really want to do that now. We will have to, if part 2 might do something funky, but I think for part 1 we can just take all the octopuses that have energy level 9 and have them flash. No, that won't work, because if we have multiple... Yeah, okay. I just talked myself out of it. So we do need to grab everything that is larger. Oh no, then we need to do the bookkeeping. Yeah. I'm gonna grab a list, highlight it, and every time we have an octopus flash, we put it in the highlighted list. And let's make that a set. Sets are awesome because they are implemented as binary trees, so looking up whether or not an octopus is flashed, so whether it's a part of this set, is logarithmic and not linear in performance. Big O notation, basically. So yeah, this is the next flasher. It can be nothing, so it's an option. Yeah, that's correct. If it's nothing, we are done. We have reached the... Oh, this is actually the fixed point condition. So if it's nothing, we can break out of the loop. Yeah, so let's pattern match on this. I don't often match on options because there's a lot of utility functions. But I think this will be very clear. If we have no next octopus to flash, we're done with this step. So what do we need to return? The grid. Can I put comments in here? And will my auto formatter like it? So if we have no next octopus that needs flashing, we say, cool, the grid or the next grid is what we currently have. Otherwise, we have an octopus that will flash. And that is actually not an octopus, that is a location and energy level. So it's a tuple. How do we keep track of flashes? For part 1, we just need to count the number of flashes, right? Yeah, we just need to count the number of flashes. So here we know an octopus flashes. So let's also make something called number of flashes. And that's the accumulating value or an accumulator, and that will keep track of the total sum. So in here, instead of saying we're done with this step, let's say we're done with this step and we had this many flashes, and this is instead of highlighted, we don't need, right? No, that's something that's only useful for a single step. So we need to keep track for every step the final state of the grid and how many flashes we had. I think that will allow us to solve this thing. So if an octopus flashes, now we need to find its neighbors. Yeah, find neighbors. In the grid we're talking about with the location of the octopus that will be flashing. What is this again? An energy level list. We did not like that. Okay, now we are back in this bad boy. So this is just basic 8 coordinates surrounding the thing. Do we want to filter out locations that don't exist, like on the edge? I think it makes sense. How do we do that? Something like this. So, okay, these are the 8 locations. Now filter out anyone where we don't have a key. And these will be the locations. So I don't know why we're in map world anymore. But that's not a problem. We rewrote find neighbors. We have no tests, so I'm just gonna test manually again. Did it not take my new definition? Why did I think putting a knot here was a good idea? Yeah, because it was not. This looks better. Let's make sure with another example. 1, 2, 3, 4, 1, 2, 3, 4. Yeah, that's better. So these are actual neighbor locations. Yeah, map here is overkill. We can do something with boundary checks and stuff, but let's not worry too much about that right now. These are now locations, yes. And we need to increment those locations. So it's a grid. No, it's a fold over neighbors with something. And let's say we feed it the grid as a state. So every step in this fold function needs to return an updated grid. I don't know how I'm going to call this function we're going to write, so I'm just going to call it folder. And that takes a grid and a location, and that just increments the energy level at that location. So that is a grid map add, I think. returns a new map. If a binding with the given key already exists, the binding is replaced in the result map. Yeah, so this add acts as an update as well. What does it need? A key and a new value. So we need to look up the value. So current level is grid. This will never crash because we already filter out locations. And we need to increase the energy level by 1. And now that I see this, it makes sense to call this increase energy level at, something like that. It does not like this. Why? What is the return type of a increased energy level? Takes a grid and a location and returns a grid. That should be what I expect, yes. Let's make that explicit because I don't understand the compiler error. Neighbors is a list of locations and then we fold over it. Yeah, what's it complaining about? Grid does not match type grip int. Where is that int coming from? Where is that int thing coming from? I don't understand what's happening here. Neighbors is a list of int tuples. We fold over it. And this is the folding function. That all looks correct. I don't understand what's happening. Oh, I understand what's happening. No? I thought, yeah. So it's complaining because we're inside a pattern match and it knows the return type of this pattern match already here. And down here we are not returning a tuple. That's what was confusing the hell out of me. Yeah, let's fix that before we continue. Oh, we have no function signature yet to specify return type. Okay, so let's stick with it just a while longer because we're almost done. These are... What are we doing? What are we doing? We have an octopus that needs flashing. We grab its neighbors. We say... Apply an increase of energy level for all the neighbors. And that's okay. I'm gonna grab this and extract that into a top level function. It's interesting enough in its own right. There we go. Grid with increased neighbors. And that's the grid with increased neighbors. And we had a flash, so we increased the number of flashes by 1. Yeah, we don't need actually the energy level of the current octopus. That is true. I forgot one thing. There's this third piece of state we need to check. And that is if this octopus has already flashed this step, we don't need to flash again. So if it has not flashed, this is what we want to do. And we want to add this octopus to the flashers. And otherwise, we... wait, otherwise this one already flashed. Ooh, this will also keep looping. I thought we were almost there and that without... I thought we were almost there, but the current algorithm, if we are going to do this recursively, this is actually something we need to do way earlier. That's what I'm trying to say. Yeah, down here actually. Okay, I'm gonna get rid of this if else. It makes sense to actually use that visited, or that highlighted set here already. So let's filter out everything that we have already highlighted this step. Except will not work because it's tuples of locations and energy levels. And we only need the entries where we are not in the highlighted set. So when looking for the next octopus to flash, we discard every octopus that has already flashed. So these are the ones that have not flashed yet. And then we look at everything with 9. I think now we're good to go. Yeah, I think we're good to go. And what is happening here? It's not a function. I'm trying to do something with it. We need to build in recursion. So at this point we do need a function to recursively call. So let's do this by defining a recursive function called take step. Why not? It takes grid, it takes highlighted, and it takes the current number of flashes we've already seen. And now this, yeah, it's still making sense in my head. So what does taking one step look like? We look for the next octopus that needs flashing. If it needs no flashing, we say done. If it needs flashing, find neighbors, bump neighbors, and record this as a flash, yes. Record the new grid, yes. And say we already visited. Why is my mouse pointer a hand? Okay. And say we already visited this octopus so we don't flash it again. There's one thing we are forgetting, and that's resetting the octopus. So everything that has a 9 or greater needs to reset back to, what was it, 0? Where are you? Looks like 9s become 0s. Yes, is this the case? Yeah, everything that has flashed has used all its energy to flash and defaults back to 0. That's something we have to do down here. But let's first build in the recursion. By calling this function recursively. Can it be that easy? Highlighted is a set of int is not compatible with. What is the type signature of set.add? Takes a value as first argument and a set as second argument, yes. I have my arguments mixed up. Or the order of my arguments. Okay. So this is taking a single step, and then we loop through it again. And this is our, like, a recursive. This is the stopping condition. When there is no more octopus to flash, we say we're done with flashing for this step. And otherwise, it looks... Yeah, it looks might be correct to me. So let's now do this part. Reset highlighted octopuses to 0. Yeah, so we need to do something with the grid. Let's do a map over the grid. What does a map for a map actually do? It takes a mapping, which is what the function we're writing now. Then it takes the Why is it called table? That's so confusing. We're in a map world, and the official MSDN documentation is mentioning the word table. Okay, but okay. So we take a mapping, a function that takes a key and a value and updates that value. So we don't care about the location. Is it a tuple or spaced? It's spaced, so we don't care about the location. The level we do care about. And that is if highlighted, if the set of highlighted contains this location, so we do need it, sorry. If this octopus is highlighted, then it's 0 again, otherwise it's just the level. So let's call it a reset grid. Let's keep the name grid in there. No types or no readable types, like the types are there, but they're inferred and not specified in the source code. Then it helps by introducing some more names. Does this make sense? We're done with this step, so we reset highlighted octopuses to 0. Otherwise, we leave the octopus alone. And I think this might be cool. Let's give it a number of steps. So are we going to wrap this into a neat function? We are. So let's wrap everything we've been doing into a take step function, which takes just a grid, nothing else. And this will nest into that outer function. And then we will call the nested function with these like helper variables. So the grid is the grid. So maybe the grid location in the argument list is not okay, but anyway. Number flashes and highlighted. So number flash is 0 and highlighted is the empty set. Cool, no compiler errors. I think that might just work. So let's give it a try. I'm just gonna run all the code I have ever written for today's problem. So I'm sure I am running the latest version of everything in my interactive window. And then let's take a look at the grid again. Yeah, we have a grid, so let's take a step. And this is the small example, yeah. Whap, whap, whap. I don't see... Oh no, everything needs to increase, right? Everything needs to increase. We're not increasing. We are only increasing right now whenever we have a flashing octopus. But that's not what the puzzle is asking us to do. First thing first, increase the energy level of each octopus by 1. And then resolve the flashing. And that's something we only need to do once per step. So now we are mixing two things. We are mixing the take one step concept and the handle all the flashes pandemic style. Where do we fill in the increase thing? Maybe this outer take step. Let's call this handle flashes, this inner function. Or no, handle resolve flashes, handle flashes. I'm gonna call it resolve flashes. So this thing does what we think it does. It resolves the flashes. Yeah. But before we do that, we need to update everything. So let's do a map.map and increase the levels by 1. Yeah. And then let's do resolve flashes. And in order to do that in a pipeline style, grid needs to be the final argument. So let's make this pipeline friendly. And in a recursive call, let's also use that order. Oh, I do wish I had automated tool support to do refactorings like this, but there we go. Now we increase everything in the grid by 1, and then we resolve flashes. That makes more sense. What do we need to return? That's maybe a good question to ask ourselves. We return whatever resolve flashes returns right now, which is the updated grid and the number of flashes. That is cool. So let's see what this gives us. 7? Did the 5 just turn into a 7? Yeah. Oh boy. Say it ain't so, say it ain't so. I think we have a bug. Let's make sure. So our initial grid is the example. Let's grab the example so we can see it a bit more clearly. 5, 4, 2, 5, 4, 2. 5, 4, 8, sorry, yeah, this is example. And when we say take a single step, what I expect is to boost every level by 1, and then only do shit when we have octopuses that need flashing. Right? So yeah, if we have an octopus that needs flashing, what does that mean? 9 or higher, yeah. We find the neighbors, we say bump their energy levels, which is also a bump. Oh, we have an increased energy level at. Maybe it makes sense to also use that here. Nah. I like the for all thing where we don't even care about the location. Okay, let's start troubleshooting. So I don't see the problem just yet, or the bug. That's the initial grid, yeah, 5, 4, 8. And there is no 9 in sight, or is there? At least for that top left thing, there is no 9 in sight. So I expect it to become 6, 5, 3, 8. 7, 7, 6, 6. I don't understand what's happening. That's never a good sign. No, my mind is completely blanking right now. How do we debug this? So we are at the stage where we're only taking a single step. A single step comprises leveling up all the levels by 1 or increasing them. And then if we have flashes, we resolve those. Let's comment out resolve flashes just for now. So now we should only be doing level increase. No, that does not look... Oh, sorry, need to take a step. So 6, 5, 9. Yeah, this looks correct. So the bug is in our resolve flashes. Yeah, makes sense because the only thing was just a one-liner. Okay, so it is maybe in here or in the pattern match. Let's see if we have any octopuses. Just gonna do some print debug of console log debug driven development kind of thing. I have never used the debugger. Oh, why is it flashing this many? It is flashing this many. Yeah. Wait. We actually do have some explosions. Let's go to the example. After step 1, we should have 6, 5, 9. Oh yeah. Am I doing the order incorrectly? First level of octopus of every octopus increases by 1, and then we do the handle flashes. Okay. So this is the original grid with a 5, 4, 8 in the top left. And then we take a step. 5, 4, 8. And we take a step and we say, hey, we want to flash. Or the octopus at 0, 2 is ready to flash. That's this bad boy. Oh no. I remember reading something about greater than 9. Why did I do equal to 9? Ah, now I feel stupid. Spent 10 minutes troubleshooting this, and it's probably not even a problem. After one step, we have 6, 5, 9, something, something, something. That sounds like it could be correct. Yeah. Will we take another step? We will take another step. See how far we get. So let's do take step and pipe this result into another take step. That will not work. No, because we actually have this accumulating variable, the, what's it called? The number of flashes. So let's do a deconstruction on that. And then we have the number of flashes is 0, and this is the next map. So let's take another step. And see what that gives us. Whoa, what's happening? 35 flashes, that sounds like a lot. 652, 35 flashes, and an updated grid. Let's take a look. Yeah, after step 1, we have nothing. 659, and then we have 880. Yeah. How many zeros are in here? Is this 35? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4. That actually could be correct. Cool. What do we need to do? Do this for 100 steps and sum up all the flashes. We can do that. How will we do that? Write a function. That's the solution for all F# problems. Write a function. What do we need? What do we need? We need to take a step, so we need a grid. So we need to do the thing we have been doing. And if n is 0, we are done. So we return the number of flashes. So if n equals 0, we're done, and we just return the number of flashes. Otherwise, we take a step, and we say, let's repeat again. And we're down one step. We're up some flashes. So it's the sum of what we had and what we just extra flashed. And the new grid is next grid. And this just keeps going until it hits 0. I think that's enough. So let's do a repeat one time with no numbers of flashes for the original grid, because we know that example a bit. Let's do 2 repeats, so then we should have flashes, and that's 35. That looks correct. I'm gonna get rid of the print statement because it will explode my console. And let's repeat this 100 times. 1656. Oh, that looks good. So we can grab our parser and parse that. actual input instead of the example. And let's run that. That's really close. I think if we brute forced today, we might have actually been faster than writing the actual logic. Cool, that is part 1 down, under our thumbs. Let's take a small resting point. So let's just copy paste and get ready for part 2. I am all out of coffee, so I hope part 2 is not too much of a brain burner. Part 2. It seems like the individual flashes are not bright enough to navigate. However, you might have a better option. Flashes seem to be synchronizing. Cool. In the example above, the first time all octopuses flash simultaneously is after step 195. So let's take a look. Ooh, that's pretty. That's pretty. In the example above, this is a very good puzzle to visualize. Maybe we might do that this weekend if we have time. Like write what is it called? Fable? Write a Fable program that visualizes this. I know there's a programming language that transpiles F# to JavaScript, so you can build web apps easily. Is it Fable? I've not played with it myself. Yeah, it is Fable. If this thing has an SVG library or something, it might be worth playing with to visualize today's puzzle. Where is the library stuff? Documentation. Yeah, looks nice. I also think there's something called Elmish. And Elmish implements core abstractions that can be used to build Fable applications. Following model view update. This looks like a really cool experiment for this weekend. So we can visualize our bioluminescent octopuses. But that's not what we're doing right now. Right now we're solving part 2 of Advent of Code. So we need to keep going, but we need to check when every octopus flashes simultaneously. If you can calculate the exact moments, that's a multiple. Oh, it's the first step. Okay, I thought we were going to have to look at pulses, something like that. Thank God it's just the first. So if you can calculate the exact moments when the octopuses will all flash simultaneously, what is the answer for the example? Is it 195? Probably, yeah. And how do we detect it? That is just a step where we have all the zeros. Everything has to be a 0. Why does that sound really easy? Will it be a performance nightmare? Let's drop back into the example world instead of our input. So we know it's 195 for this thing. Instead of repeating 100 times, we need to repeat until we encounter a stop condition. So this makes no sense. We will just loop infinitely. And we will loop and keep going. Yeah. So what changes? We always take a step except when the grid contains all zeros. So yeah. This halting condition just needs to change to all zeros. So let's figure out how many zeros we have or how many non-zeros. So that is, a grid is a map. What can we do? Do we have a map.length? Map.count? Yeah. So we can do a map.filter. Is there a map.any exists? There is a map.exists. Returns true. Yeah, that will work as well. If this is true, so we have a non-zero energy level, then we're not done. So is there a for all? There is a for all. Returns true if the given predicate returns true for all the bindings in the map. So if we have all zeros, then we are done. This is the new stop condition. We don't need, oh yeah, we don't need the number of flashes anymore. We need the generation that this is happening in, or the step. Otherwise, we take a step, we can actually ignore a number of flashes now, and we increase the number of steps we take. I don't know if we need 1 or 0 here, so let's just try something. Oh, that's not the one. This is the one. I'm gonna get rid of the number of flashes. It's not necessary for part 1, and I don't care about part 1 anymore. Was it this easy? Just the one? Yeah, just the one. Cool. So we can get rid of number of flashes. We might have an off by 1 error here, but that's easily fixed. We have a off by 1 error, so let's fix that. This is already burning CPU cycles, so I'm a bit hesitant to run this on the input. Let's give it a shot for a couple of seconds. Oh, that was actually not too bad. Hey. And we solved it within the hour? No, just over the hour mark. That's not actually too bad. I'm proud. I was expecting today, because it's a weekend day, or at least for me locally, it's a weekend day, a Saturday. I was expecting this to be a real brain burner, but the advent of code gods have spared us. Yeah, really fun puzzle. It has some really interesting twists. The pandemic spread of the flashes was cool. Cool. Let's go quickly over what we did today, and let's call it a day. We just we have our Christmas tree set up from yesterday, so I'm gonna enjoy some hot cocoa and read a book or something. But let's first take a look at what we did today. So today was a basic game of life or cellular automata style problem. I always grab for maps as data structures. I don't know why, because most of the time it bites me. It's just cool. So we parse our input into a map. Finding neighbors is something I always do the same way, and this time it bit me because we did not need values but locations. And then we spent the rest, or the better part of the hour, writing one monster function. It really is a monster function. Oh geez. That takes a step. Taking a step is a 2-step process, so we might refactor that so it's on the same level of abstraction, but we're done for the day. So 2-step process of taking a step. 1 step is bumping energy levels by 1. That's just by mapping over every element in our grid and increasing the level. And as an afterthought, or like a minor detail, we need to resolve flashes. And to resolve flashes, we use some state or some bookkeeping. The bookkeeping we keep is... Why is this number of flashes here? Yeah, that's not really useful for part 2, but to do the flash handling, we do some bookkeeping with a set of visited or flashed octopuses, and that's actually it. Yeah, that's a minor refactoring I'm willing to do to make it more clear for part 2. So how do we resolve flashes? We just do a sort of fixed point operation. Or no, I'm saying that, but it's not true. We just take a look at, is there an octopus that needs flashing? If there's none, we are done, and we just do bookkeeping for every flashed or every highlighted octopus, so they reset back to 0. But if we have an octopus that needs flashing, we find the neighbors, increase their levels, and add that octopus that just flashed to the highlighted set, so We can reset it and we don't visit it twice. Yeah, really cool puzzle. I had fun. Everything seems to still work. My brain is starting to halt, so it's a good point to wish you a good weekend. I hope you can enjoy the holiday spirit a bit, and I'll see you tomorrow for day 13 of Advent. No, day 12 of Advent of Code in F#. Bye bye.